Welcome back, students. Let's resume. In the two previous videos, we talked about how to calculate antiderivatives, but they were mostly upon power functions. This rule mostly, and in some cases, this one. Now let's talk about how to deal with exponential functions. And also, please remember the role of A in this particular case. Yeah, we're going to do these as well, but in this case, this one. Ready? Okay, here we go. Let's begin with this antiderivative computation partly as a warming up. I want you to save some time, so I brought the final answer like this. Antiderivative of e to the x staying the same. X to the e power, that's a power function, so raise the power by 1 and divide, so we get that. E to the e power, that's constant function, so e to the e power times x. X over e and e over x, they look rather confusing, but x over e is 1 over e times x, and e over x is e times x to the negative first power. So we get appropriate antiderivative computation like these. And I enhance this justification through color coding like this. Now, I'm really emphasizing this. Please do not change the order. Do not switch around. I enhance the justification through color coding here. That's because I'm a teacher. You don't have to do the color coding, but as for using this order, the same order as given, that's very important because work part should be justification. Let's see here, this way, the first term came from first, the second term came from second, third term came from the third, and the fourth term came from the fourth, and so on. That's pretty clear, even without color coding. Color coding made it better, but even without it, it's clear. So order justification and what kind of antiderivative you use, everything is here. But if you just ask computer algebra system to do the computation like Mathematica here, as you can see, they're all jumbled up. And this is typically what happens. You just use your calculator and just copy it without knowing what's going on. Of course, if you do it without knowing what's going on, that's not a credit. You're going to get credit for correct answer, which is about 30%. So in exam, you're going to get 3 out of 10. The other 7, nothing from there, because none of the justification was done. So it's very important you follow the order. You see, I did make appropriate emphasis in my answer key as well. But by the way, let me change this into the color coded. Yeah, that looks better. Before I forget, let's save this new file. Okay, let's come back. And now let's focus on these kind of problems. They are similar to these kind of problems in that we don't have any additional subtraction in denominator, so we can separate the numerator. It's a little bit complicated with all the exponentials, so let's expand the font a little bit. Okay, that probably is better. And then let's discuss these kind of problems here. So let me remind you first of what we did last time. We can separate the numerator, right? We cannot separate the denominator, but we can separate the numerator. Okay, and erase appropriately. Oops, too much. Okay, so far so good. So computation is done. Excuse me, so separation is done. And let's go ahead with simplification. The number part is of course 1/2. Now e to the what power do we have is the question. What exponent rule do we use? A to the m power over a to the n power is equal to a to the is equal to a to the m minus n power. This is what we'll have to use. So what do? 2x plus 1 minus 3x plus 2. Alright, x part. 2x minus 3x, what is it? Negative x. And then 1 minus 2, minus 1. Next, number part is 4 over 2, so it's 2. Okay. And then exponential. Now how about the exponents? Well, the usual. Let's do subtraction. X minus 3x, that's negative 2x. Negative 1 minus 2, that's minus 3. Did I do subtraction right? Be careful, subtractions are harder than additions, so sometimes you make stupid mistake. Now, number part is of course easy. 3/2. How about exponential? Oh, this is really easy. 0 in numerator, or 0 power in numerator, so subtracting. I only change the signs. Okay. The simplification is done. So let's go ahead with antiderivative computation. By the way, at this moment, sometimes students get exhausted and stop. And that's why I'm emphasizing the integral sign along with the dx. It's a good reminder. I didn't take the antiderivative yet, and I will do now. Okay, let's do it. 1/2 and then exponential stay the same. And these are all exponential functions, so they all stay the same, right? Okay, there goes my final answer. Is that right? The answer is no, not really. What is it? Well, here we go. I'm forgetting this one of A, the recurring theme of this undoing the chain rule. So what's the A value here? Negative 1, so that has to be counted in there. How about this one? Negative 2, so I need this times 1 over negative 2. Here, negative 3, so I need times 1 over negative 3. Is that complete? Yes, it is. I don't mind simplifying this thing. Let me open up the answer key and see if my computation is correct. Here I did simplification here, and 1/2 1 over negative 1, simplify, okay, 1 over negative of 1/2, excuse me. This negative 2 and negative 2 cancel out, we have plus, alright, and simplification, we get that, okay, everything is correct. This is just a simplified version of the computation I just did. So let's recap what we do. Separate the numerator, and then simplify each term, and then antiderivative each term. That's solution 1. How about the second method? Some students prefer the second method, so let me explain this. This denominator becomes like that. 2 in the denominator, stay is in denominator, that's a number part, so it becomes 1/2. Exponential part, flip it up to the numerator, so we have negative sign. And then we distribute over. So we distribute over this multiplication, so this time we're doing addition, you see. We're using this rule this time, a to the m power times a to the n power. So this is a to the m plus n power. So we're doing additions here. So from second step to third step, the computation is actually a little bit easier than previous method. Same problem, just two different methods, excuse me. So if you prefer the second method, especially here, there is some better motivation, please go ahead. I usually do it in solution 1, the first method, and so does our textbook author, but Solution 2, the second method, is also a valid method. Go ahead and do that. Well, we have some more time, so let's use the second method to do this one. Okay, alright. So how do we work this one out? Okay, we need all those parentheses here, and then okay, we have to remove some unnecessary spaces. Just a moment, please. Okay, and then what do we have? 1/2 times e to the negative 3y plus 5. Okay, including the color coding, everything is done, I guess. Does everything look okay now? Alright, now let's go ahead with the simplification. Number part first. We're distributing this 1/2 to each term. So 1/2 times 2, so that's 1. 1/2 times 4, that's 2. 1/2 times this 5, so we're going to get 5/2. That's done. How about the exponential part? We have to add up the power. So negative 3y plus 3y, oh, that's gone, so we get 5 plus 2, so that's 7 power. Next addition, negative 3 minus 2 minus 5y plus 9, and then finally exponential of negative 3y plus 5. I guess the distribution is now complete. Okay, let's go ahead with antiderivative computation now. E to the 7th power, what's the antiderivative? Oops. And then what? This is constant. So we have e to the 7th power minus y. Excuse me, e to the 7th power times y. And then minus. 2 was there before. Exponential stayed the same as always, but I need 1 over a. 5/2. Exponential stayed the same, but I need 1 over a. Let's simplify this thing a little bit. Stay the same. Okay. Stay the same, and then this one, let's simplify it as positive 2/5. And this one minus 5/6. Just some simplification through algebra. I guess now that's complete. Let me open up the answer key and let's see if this is right. Same. Okay. I don't need duplicate answers, so let's remove that. That's solution 2. We just did it. And solution 1, by the way, is the method that we used before. Separate the numerator, simplify, and then work out the antiderivative rule. Same problem, so not coincidentally, same simplification and the same answer.